Today, we're going to pull back the curtain on the magic of orthodontics. It's all about the incredible science behind the materials that build your perfect smile, from the brackets and wires to those clear aligners. I mean, really think about it for a second. How can one little piece of wire completely change your smile? How does it move teeth through solid bone? Well, it's not exactly magic, but it might as well be. It's all about material science, and honestly, it's absolutely fascinating. So let's get into it. Okay, so here's what we're going to cover. First, what's the big challenge in orthodontics? Then we'll look at the building blocks of force. After that, we'll dive into the amazing world of arch wires, see how their shape makes a huge difference, and wrap up by looking at what else is in the toolkit besides wires. All right, so what's the main goal here? What's the big challenge for any orthodontist? It all comes down to one thing: delivering a light, continuous force. Think of it like a Goldilocks problem. The force can't be too heavy, or you risk damaging the tooth. But it can't be too light or stop and start, because then it won't trigger the body's natural process of rebuilding bone. It has to be just right. That's the tightrope every single orthodontic device has to walk. So, to get that just right force, you've got to understand the three key players, the building blocks of everything we're talking about. And they are strength, stiffness, and range. These three properties basically dictate everything a wire or an aligner is going to do inside your mouth. And believe it or not, this simple-looking graph is the key to understanding all of it. It's called a force deflection curve. All it shows is how much force it takes, that's the up and down axis, to bend a wire a certain distance, that's the side-to-side axis. The shape of this line is like a personality test for the material. It tells us its whole story. First up, we've got stiffness. This is pretty much what it sounds like: how much a material resists being bent. On that graph we just saw, stiffness is the slope of the line. So a really steep slope, like climbing a steep hill, means you need a ton of force just to get a little bend. That's a stiff material. A more gentle slope, well, that's a much more flexible, easygoing material. Okay, next up is range. This is all about how far you can bend or stretch the wire before it gets permanently deformed. Before it just gives up and doesn't snap back. Think about stretching a rubber band. It has a huge range, but if you stretch a paper clip too far, it stays bent. For an orthodontist, range is everything. It tells them how far they can move a tooth with a single adjustment. And that brings us to strength. This is the maximum force a wire can take before it hits that point of no return we just talked about. This is super important because it dictates the absolute maximum force the wire can deliver to a tooth. You've got to have enough strength, otherwise the wire would just get all bent out of shape the first time you tried to eat something crunchy. And here's how they all tie together. It's almost like a magic formula. Strength equals stiffness times range. This is like a fundamental law in orthodontics. You can't have it all. You can't just crank up one of these without affecting the others. It's a constant balancing act. If you want a wire with a massive range, it's not going to be very stiff. And if you need a really stiff wire for those final tiny adjustments, well, its range is going to be pretty small. Okay, so now that we know the rules of the game, strength, stiffness, and range, let's meet the players. We're diving into the amazing world of arch wires, and trust me, orthodontists have tried everything over the years, from gold to literal space-age alloys, all searching for that perfect material. This little chart gives you a perfect overview of the big three today. You've got stainless steel over here. It's the finisher. Super stiff, super strong, but doesn't have a lot of range. It's for those final, precise tweaks. Then, way on the other side, you've got nickel titanium, or Ni. This is the workhorse. It's super flexible with a huge range, perfect for the early days of getting really crooked teeth into line. And sitting right in between is beta titanium, kind of the versatile jack of all trades. And speaking of that workhorse 90, we have to talk about this stuff. It is not your average metal. And get this for an origin story. It was originally developed for the US space program. It was named Nitinol, which stands for Nickel Titanium Naval Ordnance Laboratory. I mean, how cool is that? A space-age material is straightening your teeth. But wait, it gets even better. Not all nickel titanium is created equal. It's kind of like it has two faces. There's the classic M-Nitai, which is just really, really springy. But then there's the A-Nitai. And this is the true game changer. It's what we call super elastic. It has this incredible superpower where its internal crystal structure actually changes shape when you bend it. It's like a transformer on a microscopic level. So what does that superpower actually do? Well, it leads to this incredible property called superelasticity. It means the wire gives off almost the exact same gentle force, whether it's bent just a tiny bit or a whole lot. Remember that graph? For this material, there's a long, flat part of the curve. This is the holy grail. It's that perfect, light, continuous force we were talking about, no matter how crooked the tooth is to start with. And this chart really puts it all into perspective. Just look at the difference in range. If we call stainless steel our baseline at 1, beta titanium is already twice as good. But then look at M90. It's 3.5 times the range of steel. It's not just a little better, it's in a completely different league. This is exactly why it can handle really crowded teeth without putting on too much pressure or getting bent out of shape. Okay, but picking the right space-age material is only half the battle. Because it turns out the geometry of the wire, its shape and its size, can change the forces just as dramatically. It's not just what you use, it's how you shape it. This is where the real engineering kicks in. All right, let me ask you a question. Imagine your orthodontist takes out your wire and puts in one that's double the thickness. How much stiffer is that new wire? 2 times? Maybe 4? What do you think? The answer is 16 times stiffer. No, that's not a typo, 16. It's because the stiffness goes up by the 4th power of the diameter. That means even a tiny, tiny change in how thick a wire is has a massive exponential effect on the force. This is one of the most critical things an orthodontist has to manage. So what about making a wire longer? This is why you sometimes see those extra loops and bends in an arch wire. It's not just for looks. If you double the length of a wire between 2 points, you completely change its personality. You cut its strength in half, you make it 8 times less stiff, and you give it 4 times the range. It's a super clever trick to make a wire much gentler and more flexible when you need it. Now, of course, it's not all about wires these days. There are other tools in the orthodontic toolbox, and they all play by the exact same rules of elasticity we've been talking about. Take clear aligners. They're basically thermoplastic polymers, and they work, but their range is super tiny. We're talking about 0.2 millimeters per tray. That's why you need a whole series of them, each one taking a little baby step. Then you've got the classic rubber bands or latex elastics. They've got a great range, but they get tired fast, especially in the mouth, so you have to replace them every day. And those little power chains they use to close gaps, they start strong, but their force drops off really quickly. So it's more of a quick push than a steady, continuous force. So when you put it all together, what have we learned? That orthodontics is this beautiful dance between physics and biology. Every single detail, from the very atoms in a space-age alloy to just adding a simple loop in a wire, is a calculated, engineered decision. And it's all for one goal, to create that perfect, gentle, continuous force that safely guides teeth into a healthy smile. So here's my question for you. The next time you see someone with braces, are you just going to see a bunch of wire? Or are you going to see what's really there? A sophisticated, finely tuned force delivery system working its magic 1 millimeter at a time.